Okay, hello again. So now we're going to do I think the next to last thing, which is define the image, the kernel, and the co-kernel of a homomorphism. Recall from the last video, we defined quotient modules. So the quotient module of M by a submodule N consists of all the equivalence classes or cosets of the submodule N. And this is also a module, and it comes with a free quotient map, Q, from the original module to whatever you're quotienting it by. Okay? And then if M and N are R modules, in a previous video, we defined what it means for a function f to be a module homomorphism. It means it has to respect addition and the scalar multiplication. Okay, so we'll need those for this video. And like I said, we defined the range of a function. So if you have a function just of sets, like if I just think of M and N as being sets, then the range is all of the things that are hit by the map. So it's some subset of N that consists of all the things that F actually hits, and it might be smaller than N. But here's a picture of my function F. And it's the same definition if you have an R module homomorphism or a homomorphism between any two algebraic structures of the same type. The image is the collection of all the things of the form f of m. So it's all the things that f hits, where you let m run through the entire domain of the function. But now the new fact is that the image actually has the structure of a submodule. So let's prove that. So proof of this fact, it's an easy proof, is that suppose that x and y are both in the image of f. Well, by definition, that means that x equals, say, f of m, and y equals, say, f of m prime. So then, to show that it's a submodule, I need to show first that it's a subgroup. So if I do x minus y, I should get something that's also in the image of f. But this is f of m minus f of m prime, which, because f was a homomorphism, is f of m minus m prime. And then it's f of something, so it's in the image, because m minus m prime is something in m. So f of m minus m prime is something in the image of f. And then we also need to show that it's closed under scalar multiplication. But if I take some ring element r in R, and I look at r times x, well, that's just r times f of m. So because f was a, I don't know why I'm writing so many parentheses. Because r was a, excuse me, because f was a R module homomorphism, this is just f of Rm, and then it's f of something, so it's in the image of f. So the image of f is closed under the addition and the scalar multiplication, so it's an R submodule. Okay. Now, what the image does is, as we know maybe, is it measures how surjective the function is, and it's the same case if we have an R module homomorphism. Because if f is surjective, then if I have my map here that goes from m to n, here's n, then the things that f hits consist of the entirety of n. So I'll draw it in blue again like I did before. It means the image equals the codomain. Okay, so that's what it means for a function to be surjective. Now we have another thing that we can define for a homomorphism called the kernel. And the kernel is all of the things that go to 0. So the kernel of f is all of the m in the domain that go to 0. So f of m is 0. And this is also a submodule, because if x and y are in the kernel of f, well then f of x equals 0. I guess maybe I should use m and m prime, because I used x and y for things in n. Okay, so let's do M and M prime are some things in the kernel of F. F of X, or excuse me, F of M now. F of M equals 0, that's what it means to be in the kernel. And F of M prime equals 0. So then we want to know if M minus M prime is in the kernel. So we'll look at Fm minus M prime, but this equals F of M minus F of M prime, which is just 0 minus 0, and that's 0. So this is in the kernel. And then also F of Rm is R times F of M, because F was a module homomorphism, and this is 0 as well. So the kernel is a submodule. So we have that the image is a subset of the codomain, and in fact, it's a submodule of the codomain. And the kernel is a submodule of the domain. Now, the kernel measures how injective F is. So F is injective if and only if the kernel of F equals 0. So let's that's not a completely obvious fact, so let's prove it really fast. Oh, whoops, I'm knocking my microphone down. First, we need to show one thing, which is a fact about R module homomorphisms. Here's a fact. F of 0 always equals 0 if F is a module homomorphism. How do you prove this? I think you take, here's hopefully a proof. This is one of those ones that's tricky because there's just some trick. I think you just take F of 0 plus 0. And this is F of 0 plus F of 0, which is 2 times F of 0. Remember that the module is an abelian group under addition. So n is an abelian group under addition. And then F of 0 plus 0, if I add add 0 and 0 inside here, I just get F of 0. So what I have is that F of 0 equals 2 times itself. Excuse me. So the only time that x equals 2x is when x equals 0, of course. So this implies that F of 0 equals 0. So we always have that 0 goes to 0. That's just a property of being a homomorphism. But you might have other stuff that goes to 0, in which case your map is not injective. So now let's prove this. Now let's prove this, that F is injective if and only if the kernel of F equals 0. So to do that, we need to prove that this side implies this side. So we need to show that injective implies that kernel of F equals 0. And then we also need to prove that the kernel of F equals 0 implies that F is injective. So let's start with the first one. I'll do it in green. So I'll write this arrow to tell us we're doing the forward implication. So if we suppose F is injective, that means that for all x, y in M, F of x equals F of y implies x equals y. But then if x is in the kernel of F, then F of x equals 0. But we also know that F of 0 equals 0, because that's just a property of being a homomorphism. And so because F was injective, we have F of x equals F of 0, so that implies that x equals 0. So the kernel of F consists of only 0, because anything in the kernel has to be 0. And then conversely, now let's suppose that the kernel of f equals 0. Right, suppose the kernel of f equals 0. Then we want to show that f is injective. So let x, y be some things in M with f of x equals f of y. And we want to show that this implies that x equals y. But because f is an R-module homomorphism, take f of x minus y, and this equals f of x minus f of y, which equals 0 because they're the same. And so f of x minus y equals 0. But f of x minus y equals 0 means that x minus y is in the kernel of f. But then the kernel of f equals 0. So this implies that x minus y equals 0, because 0 is the only thing in the kernel. Okay. So that's the end of that proof. F is injective if and only if the kernel is 0. So that means that the kernel measures injectivity. If you have anything in the kernel other than 0, your map is not injective. And the more stuff you have in the kernel, the less injective the map is. And similarly, we have the co-kernel. So for a module homomorphism, or ring homomorphism or abelian group homomorphism, etc., the co-kernel is easy to define. Sometimes it's not as easy to define, but here the co-kernel of f is just the codomain divided by the image. And so we know since f is surjective if and only if the image equals the codomain, that says that the co-kernel of f equals 0 if and only if f is surjective. So the co-kernel also measures how surjective f is, and if it's 0, your map is surjective, and if it's far away from 0, your map is not very surjective. So now we can write this chain of maps. This is going back to some things we've done in previous videos. So we know that because the kernel of f is a submodule, we get a free map that's the inclusion map of that submodule into the bigger module. And so we get a map I from the kernel of f included into M, because it's a submodule. And so sometimes people will write the hook right arrow to say that it's an inclusion. And this is an injective map. Inclusions are injective homomorphisms of modules. And another way to say that it's injective is to write a 0 on the left here. That just means it's surjective. That's why there's a 0 there. And then we also have the free map because we took a quotient. If we take a quotient of n by something, we get a map. So the co-kernel of f is a quotient of n. So we get a q from n to that quotient, a quotient map that just takes every element to its equivalence class. So that's this map, and it's surjective. So we can always take this map and put a surjection after it. By the way, if we put an arrow on the right, that indicates that it's surjective. Or you can write this double arrow here, or both if you're really extra. So you have your original map F. You can follow it by a surjection, and you can precede it by an injection all the time. That's something you can always do. So now let's do some examples of R-module homomorphisms. Our first example will be Z3 to Z3. And remember, this is like these are Z modules. So we can define f of x, y, z equals x0, 0. you can check on your own that this is a Z module homomorphism. And in like matrix form, maybe you can write it as 1, 0, 0. It's like this matrix, because if I multiply it by x, y, z, I get x, 0, 0. So sometimes you can write it in this matrix form. We want to compute the kernel, image, and co-kernel of this. So what's the image first? The image of f is all of the things of the form f of x, y, z. So all of where x, y, and z are integers. But then we just get things of the form x, 0, 0, where x is some integer. So the image of this map is isomorphic to z as an abelian group. Okay, and then the kernel is all of the things that go to 0. So what goes to 0 under this map? Certainly 0 goes to 0, and that's good because otherwise it wouldn't be a homomorphism. But other things that go to 0 are anything of the form 0, y, z. All that stuff goes to 0, and in fact, it's the only stuff. Because I can't put any non-zero thing in the x slot and have it go to 0. So this is basically isomorphic to Z2 because I have 2 slots that are filled by elements from Z. So that means that the map is definitely not injective because the kernel is non-zero. So the kernel is 2-dimensional. And then the co-kernel is just the codomain, which is Z cubed, divided by Z to the 1. And this is isomorphic to Z squared. So both the kernel and the co-kernel are isomorphic to Z squared. And so if we write down like our little series of maps, we have our injective one from the kernel to the domain. And then this is the map we started with. It's like the matrix 1, 0, 0 with Z coefficients. And it goes to the codomain, which is Z cubed. And then we have this surjective map to Z squared. And that's it. That's the co-kernel. All right, now let's do another example. This one, so this one was neither injective nor surjective. It had a non-trivial kernel and a non-trivial co-kernel. This one looks like it might be injective. It's an inclusion of R into R3. It's defined by f of x equals x, 0, 0. So it's an inclusion. So let me draw R3 here. Here's R3. It's the inclusion of the x-axis. So here's the, let me label my axes. Here's x-axis, here's the y-axis, here's the z-axis. So here's the x-axis. This is the copy of R to the 1. And then the black axes are the copy of R3. So this is the map that includes the x-axis into the 3-dimensional Euclidean space. So it's injective, is what I'm trying to say. So the image of f is the x-axis. It's also all the things of the form x, 0, 0. But this time where x is in R. So it's the x-axis. The kernel, what's the kernel? What things go to 0? Well, anything that's on the YZ plane, this plane, everything on this plane will go to 0. So the kernel of f equals the, oh wait, sorry. No, my bad. Yeah, let me write out, sorry. These are the x in R such that x, 0, 0 equals 0. The only one of these is 0. So this is an injective map, which it should be because it's an inclusion of a subspace into a bigger vector space. So it's an injective map. And then the co-kernel, what's the co-kernel? The co-kernel of F is the codomain, which is R3, divided by the image, which is R. So it's isomorphic to R2. And this is the ZY plane. So the co-kernel is what you obtain by squishing this orange copy of R to 0. So that means that all the vectors with any x component get projected onto the YZ plane. So the co-kernel looks like just this ZY plane. Just this plane. It's a copy of R2. Okay, so there's an example with vector spaces. So example 2, I guess that was example 1.5 because it was similar to example 1. Now here's one, a map from Z to Z. This is going to be pretty much, this has been a canonical example for us like the entire time. This is an abelian group homomorphism, it's a ring homomorphism, it's a module homomorphism, it's all kinds of different homomorphisms. So this map defined by multiplication by 5. So what's the image of this map? The image of F is all of the things of the form 5x, where x is in Z. So this is what we called last time 5Z. It's all the multiples of 5. The kernel of F is all of the x such that 5 times x is 0. Well, there's only one of those, it's 0. So this is another injective map. Multiplication by 5 is injective. And then the co-kernel of F is Z divided by 5Z. Which as I didn't mention last time, but this is the group with 5 things in it. It's the integers mod 5. I think we defined those in some previous video. Integers mod 5. It's the same thing as Z mod 5Z, that quotient group. And so we have 0 goes to 0, which is the kernel. So this 0 was redundant. We can get rid of it. 0 goes to Z, which goes to Z again. And this is multiplication by 5. And then this goes to the co-kernel, which is Z mod 5Z. Now, sometimes it's also nice to factor this this quotient map. So if I look at the quotient map, the kernel of the quotient map Q from Z to Z mod 5Z, what is that? What are the things that go to 0 under the quotient map? Well, they're all the multiples of 5 because those are all the things that are being killed in the bottom of this quotient. So the kernel of that is 5Z. So we also have this sequence where 5Z is the kernel, and then you have this map. Here's Q. This is the inclusion of the kernel, and here's kernel Q, which goes to Z mod 5Z. And this is already a surjection, so adding another 0 here doesn't help. But you get this sequence as well. That's something that comes up all the time. Okay. So now let's do the last example, which is back to this teaser type thing, or maybe the last thing we'll do. We were in the previous video, we were trying to look at the quotient of this polynomial ring or polynomial algebra by the ideal generated by x squared plus 1. And eventually we're going to show that this is isomorphic to the complex numbers. So to do that, we'll define a map. And this will be a map of algebras, or or rings or whatever, defined by p of x goes to p of I. So how does that work? If I have a polynomial, a real polynomial, maybe like 3.1 plus 4x minus 2i or something like that. Or sorry, I'm jumping ahead. Minus 2x squared, maybe like plus x cubed, something like that. This map f is going to replace all of the x's with i's is what it's going to do. So this real number will be left alone. Then we'll get a 4i, and then we'll get a minus 2i squared and plus I cubed. And then I have 3.1 plus 4i, and then plus 2, because I squared is minus 1, and minus 1, because I cubed is minus 1. So all in all, I get 4.1 plus 4i. Just for this example. So it takes a polynomial, it replaces the coefficients with the variable x with the complex number I. It's some sort of evaluation map. And its evaluation maps are always algebra homomorphisms, because if I take p of x minus q of x, for instance, f maps this to p of I minus q of I. But this is the same thing as the map applied to p of x minus the map applied to q of x. And if I take a real number little r and multiply it by q of x or something, the map f takes this to the real number times the complex number q of I. And since the complex numbers are a real algebra, you can multiply complex numbers by real numbers. It just multiplies both the real and imaginary part. And then I can also multiply polynomials. P of x times q of x maps to p of I, q of I. And it respects this multiplication as well. So this is really an R algebra homomorphism. But you can think of it as a module homomorphism only, or only like only a vector space homomorphism, I mean, or only a module homomorphism, or whatever. I think we'll mostly think of this on the level of rings, because we're just thinking about this ideal. Okay, but we want to compute, we're trying to compute the image, the kernel, and the co-kernel of this. So let's look at that. First, I claim that the image of this map is C, complex numbers, the whole thing. So it's a surjective map. So if I want to show that, I have to take given a complex number a plus bi in C, I need to find a polynomial that maps to it under this map, but I just take a plus bx, and that maps to a plus bi when I replace the x with an I. So given any one of these, I can find one of these that hits it, a polynomial. So f is surjective, and so in particular, the co-kernel of f equals 0. And then the kernel, let's look at the kernel of f. The kernel of f is all of the polynomials so that when I plug I in, I get 0. Now that's not as easy to compute. I think I need something that I should have done before, but you probably forgot. So let me try to really briefly, polynomial long division is what we need. So remember, if I'm trying to divide a polynomial p of x by another polynomial d of x, I can try to do this by long division. And if there's no remainder, I get just some polynomial. But maybe d of x doesn't evenly divide p of x, in which case I get a remainder term, like r of x divided by d of x. I get some fractional part of this. But when we divide, the degree of the polynomial r of x becomes less than the degree of whatever we divided by, the divisor, d of x. So for any polynomial, p of x, I can always write it as q of x times d of x plus r of x, with the degree of r being strictly less than the degree of d. And I can do this for any d that I pick. So I'm going to apply this. I'm going to apply this. I want to show that everything in the kernel of x, my claim is that everything in the kernel of x is something in the ideal generated by x squared plus 1. So I guess the first step is show that x squared plus 1 is in the kernel. X squared plus 1 is in the kernel of f. This is because if I apply f to x squared plus 1, I get I squared plus 1, which is 0. So that implies that if I take x squared plus 1 times any polynomial, q of x, that also maps to 0. So the ideal generated by x squared plus 1, meaning any of the polynomials with x squared plus 1 as a factor, like this one, they all map to 0. So the ideal generated by this is contained in the kernel of f. But then we want to show also that the kernel of f is contained in the ideal generated by x squared plus 1. And to do that, we need the division algorithm. So suppose that p of x is in the kernel of f. Use polynomial long division and take p of x, let d of x be x squared plus 1. And then I can write p of x equals x squared plus 1 times some quotient q of x plus some remainder term. But the remainder term now is less than 2, because that's the degree of x squared plus 1. So r of x has to be a degree 1 polynomial. It has to be ax plus b for some real numbers a and b. But then, let's see. Then take f and apply it to p of x. Oh, wait, no. We already know that's 0. So if I take f and apply it to p of x, it should be 0. But f of p of x equals I squared plus 1 times q of x plus r of I. And this should be a q of I as well. I have replaced all the x's with i's. But this part dies because it's I squared plus 1 times something. And so this is just a plus bi. So this tells us that a plus bi is 0 as a complex number. And the only complex number that's 0 is the 0, 1. So that means that a and b are 0. So that implies that to begin with, r of x was 0. Which means that x squared plus 1 evenly divided p of x. In other words, p of x was x squared plus 1 times q of x, which is exactly what it means for p of x to be in the ideal generated by x squared plus 1. Okay, so I think that's the end of the video.